Hello and welcome. In this video, we are going to use flow state test steps to evaluate flow properties. Well, it's assumed that you have already gone over this particular video builds upon the evaluation of properties using closed system test steps. So without repeating what we have covered in that video, let's go and get started with the examples of a couple of animations. So we have already seen what is a system state looks like. A system state builds upon the core thermodynamic states, and we add some system properties such as system mass, system energy, etc. As opposed to this, a flow state, which describes the condition of a flow, builds upon again the core thermodynamic state, adding flow properties such as entropy flow rate, volume flow rate, etc. Obviously, as I already mentioned, the core thermodynamic state is shared between the system state as well as flow states. Okay, so without further ado, let's get started. Let's make up a simple problem of this expansion valve where a fluid comes in, let's say refrigerant, and its pressure drops because of friction. We'll assume the flow energy remains constant because there is no heat transfer or work transfer. And so with that conditions, let's see if we can figure out the two states. Okay. So to get started, we go to the test steps page. The flow state is our destination, and we'll use the PC model because we'll use a refrigerant in this case. Once again, whatever model you launch, you will find a number of examples, and this library is increasing in size. These are video examples as well as test codes examples of how to solve a problem involving a flow state. So here is the flow state, which looks almost similar to a system state test steps. Now, to calculate the inlet state, let's assume the refrigerant R134A is coming at, let's say, 1000 kPa, and let's say at room temperature 30 degrees Celsius with a mass flow rate of, let's say, 10 kg per second. We calculate the state, and then we notice that as we calculate the state, the picture of the flow will change depending on the pressure and temperature. It tells you visually how the state looks like. So for state 2, we'll assume that the pressure has drastically been reduced by the expansion valve to 100 kPa, and during that expansion process, we'll assume there is no change in the flow energy, which means J2 must be equals J1. Also, excuse me. Also, the mass flow rate cannot change because of conservation of mass. So that evaluates our second state. Notice the temperature has drastically dropped. If you go to graphics panel, you can see state 1 and 2. This is our constant energy line. Some people call it constant enthalpy line. You'll also see the vapor dome, the saturation line. The saturation line data is shown here. The saturation data can be copied and pasted for further analysis, and the calculated state properties appear in the table below here. All the properties are listed that has been calculated. Of course, a super calculator will generate a textual output of the entire solution right here, and as we already discussed, the test codes which can be used to regenerate the solution. Well, the I/O panel can be used for a lot more things. For instance, we can calculate some secondary variables. We click this button to show only our user codes. So let's say we want to calculate, not kinetic energy, but let's say we want to calculate how much entropy is coming in. S dot 1 equals M dot 1 star S1. S dot at 2 equals So as you can see this entropy flow rate. I've defined two new variables. Um, Entropy flow rate at the exit is higher than at the inlet. That can be used for understanding how entropy is generated in this expansion valve because of friction. Other use of this I/O panel could be, suppose we define a pressure P at the exit to be equals, say 200 kPa. It has to be in English, in SI units. So we have defined a new variable called P exit, which can go back to the state panel. And instead of assigning a hard number, we could just use P2 equals P exit. That's the variable we just defined. So the answer is recalculated for exit pressure of 200 kPa. If you put the pointer over, you can see its value appear right there, 200 kPa. The advantage of that is that to do a parametric study, it becomes so simple. You can just go there and say, what if the exit pressure was 400 kPa? And all you have to do is to calculate to register the change and super calculate to update all calculations. Anyway, the purpose here is not to go into the details of an individual flow state test steps, just to show you that there are so many different models you can use to find the flow state of different working substances. Again, as you go to a particular model, you'll find examples, video examples on the hands-on examples page, and that can guide you to understand how to use a particular flow state test app. Thank you.